So, last week we talked about how our linear regression is essentially like a sample value. We have an entire population of data out there, and the values that we have on our scatter plot are thought of as being a random sample of that population's data. So when I come up with a regression model, that's like one individual in the sample. Okay? John could have his own regression model. Each person in this class could have his or her own regression model that is going to be describing, in theory, some population model that exists between these two variables. So we have a way of representing our sample models. Okay? Y hat equals A plus BX. Remember, A is the y-intercept, B represents the slope. And we use those because here is the representation of that population regression model. Mu sub y equals alpha plus beta x, where alpha and beta are the population parameters for these sample statistics right here. Alpha is the population model's y-intercept. Beta is the population model's slope. Okay? So A and B, alpha, beta. Now, what's happening here is that, let's say we substitute some value of x into our model. Okay? We were talking about that example of the newborn babies crying and that possibly leading to a higher IQ later in life. Okay? We will revisit that example in a few minutes. But let's say I have an x value of 12. I substitute that into my model. It spits out a y value. Same thing with John and his model. Same thing with each of you in all of your individual regression models. Now, what this is saying is that we substitute an x value in, we expect that y value to be pretty close to what this population model would spit out. Some of the values are a little lower than what we expect. Some of the values are a little bit higher, but they vary in a normally distributed way. So we'll talk about that distribution in a minute. But all of those y values that we each get from our own models, if we were to average them all out, it should become that population model. Right? That's why we use mu, because it's the mean of all theoretical possible outputs. Now, we had said that these possible y values, they fall into a normal distribution. And the normal distributions, no matter what x value you substitute in, they are all identical. In that the mean of all of those y values is the exact line that's spit out by the population model. That goes at the center of all of those bell curves. But a bell curve has a standard deviation, we're calling it sigma. The standard deviation of every curve, no matter what the x value is, that is constant throughout the function. Okay? So this is referred to as the standard deviation of that regression model. Now, this is another population parameter, just like alpha, just like beta, just like the sigma that we saw several weeks ago, and the mu that we saw several weeks ago. These are population parameters that really we don't know what their value is. So the best we can do is use a sample statistic in their place to kind of serve their purpose and represent what's going on. So in this case, we are using standard error, okay, lowercase s, to represent that. Now, this is not an equation you need to use. We're relying heavily on the technology in this chapter, pretty much every equation that you see is not something that you will do by hand. Just kind of expressing what this is. Okay? This sample standard deviation, or this regression standard error that we are going to use in place of sigma, it's found with the residuals of the y values, and add them all up, multiply by 1 over n minus 2, take the square root, that is your regression standard error. This is a calculator value that is provided to us. We can also get it from Excel. I'm going to show you today. We said that GeoGebra, we've kind of reached our limit with its statistical capabilities, but I'm going to show you how Excel can kind of step up its game, and we can use that if it's a little easier than the calculator in a lot of cases. Okay? I'll show you that at the end. All right, so in this case, this is the Minitab output. This is another statistical software package. This is the standard error in our example of the crying leading to a higher IQ, 17.5. Here's our regression model again, an intercept of 91, a slope of about 1.49. This was that calculator output that we saw at the end of class on Thursday. Our expected standard error of about 17.5 contributes to that. All right, so let's talk about the actual hypothesis test. Before I get into this, any questions on any of that background stuff before we get into this? Okay. Now, the actual t-test, we saw it when we did our calculator work last week. It gave us a t-statistic, it gave us a p-value, but we never actually talked about what the hypotheses are. Well, the null hypothesis is going to be in reference to the slope, because the slope is the defining characteristic of a line, right? It's the unit rate. It talks about its rate of change, okay, the steepness of that. So everything about a linear model is in relation to its slope. So the population slope is represented by beta. And our null hypothesis for every one of these tests is going to be beta equals 0. Because the slope and the correlation R, they are like intertwined with one another. Remember, if you have a positive slope, you have a positive R value. Negative slope, negative R value. If you have a slope of 0, you have a horizontal line, which means that you don't have a positive or negative correlation. You have an R value of 0. So think about what this is saying. When you have a null hypothesis, where you're saying the population model's slope is 0, in other words, you're saying that there is no linear relationship in the population for this data set. Our alternative hypothesis, I'm going to jump down here, you're saying, either one-sided or two-sided, that the slope beta is greater than 0, meaning that you have a positive relationship, you have a positive correlation, or beta is less than 0. You have a negative slope, a negative relationship. Those are one-sided alternative hypotheses. You could also have a two-sided alternative hypothesis and say beta is not equal to 0. That makes a little bit less sense in the context of regression. Now, I said this is going to be a t-test. So our t-statistic, you're not going to calculate this by hand. However, if you were, the procedures are still the same that we saw when we first started calculating z-scores months ago, where you're doing observed minus expected all over a standard deviation measure. Okay, a sample value minus the population value divided by a standard deviation value. We have that here, but instead it's written as b, the slope, divided by standard error of the slopes. This is not the same standard error that we just talked about. it's a whole nother thing. Okay, it's this, which is again another reason why we're not going to do this by hand. All right, you take that sample, standard error that we did just talk about. It was 17.5 approximately, and you are dividing by the square root of the sum of the squares of all of the x differentials. Okay, so your individual x value minus the mean. Okay. That is something that is also provided for you by the Excel output, okay, or they show it to you here in their software package. It's going to be the standard error of the cry count, which is the x values. Okay, how many times did that baby cry? Okay, in this case, the value is about 0.487. We also have it from the Excel output right there. Okay, and again, I'll show you Excel in a little bit. Anyway, this t statistic is the same as doing b, your model's slope, minus beta, the population model slope, divided by this standard error of b. But it can be simplified to just b over the standard error, because our null hypothesis, our population value, is saying that beta is 0, that there is no slope. So every single time that beta value is going to be 0, you just have b in the numerator, which is why they simplified to just b over the standard error. Again, the calculator, Excel, it will do this for you. I just wanted to show you that nothing is changing in the procedural accomplishments of this t-test, right? You're still following this sample value minus population value divided by standard deviation. We see that here. Okay, it's just the values are a little bit more difficult to obtain. This direction of the alternative hypothesis, keep in mind that when it is two-sided, you're looking at both tails. And this t-distribution is symmetric, so the p-value here is going to be twice that of if it were a one-sided test. That is important for the Excel output. I'll show you in a little bit. The Excel output will only give you a two-sided p-value. There's no way to indicate the direction of the hypothesis there. So if it's a one-sided alternative hypothesis, you need to divide that p-value by 2. All right, so back to our example. We thought we had a positive correlation between the number of crying incidents, the cry count, and the IQ of that child. So our null hypothesis says beta equals 0. The crying has no straight line relationship with IQ, but we conjecture that there is a positive relationship. So we're going to go with a one-sided alternative hypothesis. Again, most of the time when you're doing linear regression analysis, you're going to have a one-sided alternative because you believe that you have a positive association or a negative association. Very rarely do you walk into this, let me throw it up against the wall, see what sticks. Is there any relationship, positive or negative? Now, we saw the scatter plot. We believe there is a positive relationship. They show the calculation of this test statistic by hand. There is our model slope, 1.49, divided by that standard error of the crying that I had mentioned, about 0.487, corresponds with a t statistic of 3.07. And remember, on our t model, it is symmetric. Right here at the center is the 0 that we expect from our null hypothesis. We are more than 3 standard deviations above that. So the p-value that corresponds with it is pretty small. Okay. Again, on the statistical software output, they give you the two-sided 0.004. We want one-sided, so you divide that by 2, 0.002. Reject the null, accept the alternative. We have evidence that there is an actual positive relationship in this population. Questions on that? I've pretty much said this. Just again, showing that relationship between the slope and the correlation R. Okay, they are closely related to one another. The slope beta of the population regression line is closely related to the correlation between X and Y in the population. So when you are setting this null hypothesis as beta equals 0, it is therefore exactly the same as testing that there is no correlation between X and Y. Okay. Now, because the slope is such a critical value, we would like to estimate with some precision what its actual population value is. Remember, this 1.49 that we've been using, it's just our sample's slope. It's not necessarily what the actual population slope is. We don't know what that parameter is, but we can calculate a confidence interval, 95% confident, that the actual slope for that population's model is between this and this. So, again, they show you how to calculate this by hand. We're going to go with the calculator. I'll show you that in just a second. But procedurally, it's the same kind of thing as what we've been doing for every other confidence interval. We have our estimate, in this case 1.49, plus or minus our T star. Okay, that can vary based off of the degrees of freedom. So it's a little bit, it's not like we're going to just use the same T star for every 95% confidence level here, because each of our problems can have a different number of degrees of freedom. And then that standard error estimate that, again, we are not finding by hand, so you let the technology provide that for you. They show this calculation here by hand after you've had the statistical software provide you with these bits and pieces. There is our estimate, the 1.49. Here is our standard error value. And the degrees of freedom, we had 38 individuals in our sample. We have 2 variables, so we're doing n minus 2 for the degrees of freedom. That's 36. So you'd have to look up on a chart what the T star value is for 95% confidence and 36 degrees of freedom. Why would you do that? If you're letting technology spit this stuff out to you, you might as well let it calculate the confidence interval for you. Okay? Which is what we're going to do. Either way, get a confidence interval here about 0.5 to 2.5. We are 95% confident that the mean IQ increases between 0.5 and 2.5 points for each additional peak in crying. That is the slope, the population model's slope. Any questions with that? All right, last slide here. Again, to use these inference procedures, what we're doing is fitting a line to 2 sets of quantitative data. And theoretically, you could do this for anything. Okay? You could have the most random scatter plot there is and try to fit a linear model to it. Some are good fits, some are not so good. But we have to have an idea that this is actually a relationship that exists in the population for these procedures to make any sense. Otherwise, that fitted line may be almost useless. So, a good first step is to verify by looking at the scatter plot that it appears like we have a linear relationship. Now, if you remember, we didn't have a terribly strong relationship in our sample. the R value is only like 0.45. Okay? That's our sample value, one of a theoretical possible like infinite number of samples out there. So we're going to go with it and test to see if a linear model could exist in the population. Other things that we need to kind of confirm, those response variables. The response varies normally about the population regression line. That was saying that all of those individual bell curves about our model, okay, that it varies in a normal way. That's kind of hard to check unless you're looking at a bunch of models. This is a little bit more logical here, that you have independence with the observations and that standard deviation of those normal responses, that they are all the same. One way to help you with this is to kind of check that residual plot. We talked about that on Thursday a little bit. Remember, when you're looking at a residual plot, you're looking at essentially the line of best fit is now serving as the x-axis. And the residuals are the differences between all of those y values, okay, what you got from your model and what you would expect based off of your model. Or, I'm sorry, I said the same thing. What you observed from your data set and what you would expect for that x value from your model. So, you're expecting the appearance of randomness on your residual plot. Half of them are going to be above the x-axis, half are going to be below. Okay? You don't want to see any like distinct curves or parabolic shapes or anything like that. That's indicating that this is not a linear model and that it's something else. And ideally, you'd like most of your values to be pretty close to that x-axis, okay? Meaning that the residuals are pretty small. Okay, I'm going to flip screens. We're going to take a look at how the calculator will do this and how GeoGebra will perform this. Not GeoGebra, Excel will perform this for us as well. So, get this going. Okay, so on the calculator, we're going to our stat and over to our tests menu. Again, this is why after we have all of our data entered into L1 and L2 on the calculator, we're jumping all the way down to our second to last two options, linear regression t-test and a linear regression t-interval. Now, we had already shown you what the results of the t-test looked like last week, but we didn't really look at the hypotheses to interpret the t-statistic and the p-value. So on this screen, we're just confirming we have our data in L1 and L2. Also confirm that we have our one-sided alternative hypothesis. In this case, we're testing that beta is greater than 0. If you want to put the regression line into y equals, you can, but go down to hit calculate. And we get a t-statistic of 3.07 approximately. And here's our p-value, 0.002, less than 0.05. Reject the null hypothesis, accept the alternative. We do have convincing evidence that we have a positive linear relationship here. There's that degrees of freedom. Remember, we said 38 individuals in our model. N minus 2, because of 2 variables, gives us the 36 degrees of freedom. This will also do our regression analysis for us, okay, the A and B values of our model. S is that standard error for the Y values, that 17.49 that we had mentioned. If you were to need that, that's there. But again, let the technology take over. R square and R are also provided there as well. For the confidence interval, again, stat tests, second to last on linear regression t-test, confirming L1 and L2, your level of confidence there, 0.95. You don't really need the Y1 in there, but hit calculate. There's that 95% level of confidence for the slope. We're 95% confident that the actual slope of that population model is between about 0.5 and about almost 2.5. And once again, it does the regression analysis for you, gives you the actual B value, gives you the intercept. There's that standard error, degrees of freedom. If we scroll down, it's R and R squared as well. Questions with that? The very last thing is with Excel. Now, we're using Excel because Google Sheets has a similar add-on, but to do this, we need to get some approval from the tech department, and you guys have Excel. This is just easier, okay? But anyway, with Excel, I have our data set entered in here, 39 rows. We have our heading in the first row, so 38 individuals. Again, I got this from all of those data sets that were provided with the textbook problems. Okay, I have it linked with your homework assignment that you'll take a look at in a few minutes here. They're also linked from the textbook button on the Canvas homepage. So, what we're going to do the first time is you're going to enable this statistical analysis sub-package in Excel. Okay? So, if you're in Excel, under this data tab right here, you're going to go over to analysis tools. There's a button that looks like the gears. And I have two options available. You might have others. You could browse for more. If you don't see this, then you're probably going to want to browse for the analysis tool pack. Check that box, hit OK. And once you've enabled that, you're going to select our data, just like that, and you'll have this data analysis button available to you that we will check. And what it does is it enables an alphabetical list of all of these statistical tests. Okay? We're going to talk about ANOVA in our last lesson of the year, but you see correlation, covariance, descriptive statistics. Most of these should be familiar to you. Histogram, rank and percentile, t-test, z-test at the bottom. We want regression. So we're going to select regression, hit OK, and it's going to open up, just confirm where your data is for the Y and the X values. We have some checkboxes here that we could enable or disable. I do have labels in my highlighted data set. I do want it to provide me with a confidence interval of 95 confidence. And I would like it to give me the residuals and a residual plot, and I want this to be created in a new worksheet. Okay, you could also have it entered in the same sheet. So I already have mine created here, and this is what that output looks like. Pretty thorough analysis. We get the R value, the R square value, that standard error that we talked about, 17.5 approximately, 38 individuals in our sample. We also have 36 degrees of freedom. These aren't really relevant to us right now, but we'll talk about ANOVA later this week. This is an important box for us right here. The coefficients. These values are giving us our regression model. Okay? The 1.49 is the slope for our regression. It's our b value. The 91.27, that was our y-intercept. Okay, so you substitute those two coefficients in to create your linear model. Here is that standard error of the slopes that we had mentioned. We used it as part of our t-statistic calculation and our confidence interval calculation, the 0.487. Again, if you were to need it, that's where it comes from. We have our t-statistic of 3.07 approximately and our p-value. Now again, I said that Excel will only find two-sided alternative hypothesis p-values. So that 0.004, we need to divide that in half to get the 0.002 for our one-sided alternative hypothesis in this case. Notice that there's also a t-statistic and a p-value for the intercept. That is also a calculation that can be done. It's less applicable, less relevant here, but it kind of speaks to the strength of the correlation and the prediction power of your model. Those statistics are available to you there as well. Lastly, we have our confidence interval for our cry count, which is our slope. And we see our values here, the lower boundary and the upper boundary, 0.5 and about 0.248. I also had it spit out the residuals for us, okay? Our predicted IQs based off of each of our individual observations. Okay, we could pull those individuals up if we wanted. Here are the residuals, and here is the residual plot if you needed to analyze that. Again, you're looking at kind of the appearance of randomness. Half are going to be above, half are going to be below. Any questions with that? So Excel kind of does a nice job in stepping up to fill the hole that GeoGebra left us with. All right. So let me stop this here.